Okay, you've made it to the last video in week 12. Elsa is draining an aquarium. The graph shows the amount of water in liters in the aquarium versus time in minutes. All right, let's take a look at this. So this is our graph. We see time in minutes is getting bigger. 1, 2, 3. It looks like it's going up by a minute. The amount of water in liters looks like starts at 600 liters, and then every single minute it's definitely coming down and decreasing, which would make sense if you're draining an aquarium, right? It's going to take a few minutes for it to drain. And it looks like it started at 600 liters of water. So that's a pretty big aquarium. Okay, let's look at these questions. At what time does the amount of water in the aquarium reach 0 liters? Okay, at what time? So they're asking you to figure out what time does the amount of water in the aquarium reach 0 liters? So if you guessed 5 minutes, you are correct because once you got down to 5 minutes here, the aquarium had 0 liters in there. Choose the statement that best describes how the time and amount of water are related, then fill in the blank. All right, so we have two options. We have this option here, option 1, option 2. Let's separate that. As the time increases, the amount in the water in the aquarium decreases, or as the time increases, the amount of the water in the aquarium also increases. So hopefully you're thinking it's option 1, right? As the time increases, the amount in the water is not increasing, it's decreasing. So we're going to stray away from this option. So we're going to choose this option. And then what's the rate that the amount of water is decreasing? Okay, so the rate is going to be your slope, which is rise over run. Okay, so you can think about this a couple different ways, right? You could put a point here and then kind of come up and find your next solid point. Come up and find your next solid point. Shoo, you could do that. And take a look at your slope from there. That's what I might want to do. You could also just pick 2 points, do your slope formula if you want. I'm going to start with maybe thinking about this point here, and then I'm going to go up 2 hops. Well, when I go up 1 hop, I'm going up 60 liters and another 60 liters. So I'm rising 120 liters. And then I'm running, well, from 5 to 4, there's a 1 minute difference. Okay, so my slope is decreasing at 120 liters per minute. All right, let's take a look at another one. Owners of a recreation area are filling a small pond with water. Let Y represent the total amount of water in the ponds in liters. So Y is the total amount of water in the pond. Let X represent the total number of minutes that the water has been added. So X is time. So X equals time, Y equals liters. Suppose that X and Y are related by this equation. Let me write this bigger. 29X plus 700 equals Y. Answer the questions below. Note that a change can be either increasing or decreasing, right? You could have either a positive slope or a negative slope. For an increase, use a positive number. For a decrease, use a negative number. What is the change per minute in the amount of water in the pond? That's going to be our slope. What's the starting amount of water in the pond? That's our y-intercept. All right, is this written in slope-intercept form? Remember, slope-intercept is y equals mx plus b. Well, kind of, just kind of feels a little backwards because instead of y equals, that's at the end instead of the front. But we know that every number that's the coefficient in front of x is your slope. And we know that this is your y-intercept. That's your b. That's your y-intercept. Okay, so what is the change per minute in the amount of water in the pond? Well, we know it's changing at 29 liters. The change is your slope. What's the starting amount of water in the pond? Well, that's 700. So if you were to kind of graph this out, right, they're filling a pond with water. And you don't have to do a little graph, but I just want to kind of show you that as the time is increasing, right, and they're filling a pond, the pond is also, here's your liters here, it's getting fuller and fuller and fuller, but it started at 700 liters. And then for every minute that's passing by, it's increasing by 29 liters. All right, let's look at another situation here. Oh, we're going to construct a scatter plot. Okay, these are fun. Let's see if I can make this better here. The table below shows the amount of rainfall and the temperature at noon in each of 6 cities. Create a scatter plot for the data. Okay. Well, a scatter plot just means we're going to plot these points, but we're not going to connect the line. So we're going to plot the points, but then don't connect the points. Okay. So on our x-axis, we have amount in rainfall, and the y-axis is the temperature outside. So we're going to label this. This is our x, and this is our y. So we're just going to put these points on. At 1 millimeter of rainfall, the temperature is 13 degrees. Okay, so we're going to go down and find 1 millimeter of rainfall, and the temperature is 13 degrees right there. At 3 millimeters of rainfall, the temperature was 10. So we're going to find 3 and 10. At 6 millimeters of rainfall, the temperature was 8. 6 millimeters of rainfall, temperature is 8. At 8 millimeters of rainfall, the temperature is 5. So here's 8, temperature is 5. At 9 millimeters of rainfall, the temperature is 3 degrees. And at 10 millimeters of rainfall, the temperature is down to 2 degrees. So we have built a scatter plot. So just don't connect those. This is just a scattering of data points. So you could kind of visually see that as more and more rate comes down, the temperature is falling, right? So this is negative here. So as the rain is increasing, right, in millimeters, the temperature is decreasing. So that's a scatter plot. Let's talk about scatter plots and correlation. The scatter plot below shows the time spent texting and time spent exercising by each of 21 students last week. Also shown is the line of best fit. Okay, so someone has created a scatter plot, and then the line of best fit is this line right here that a computer or a program, or apparently Excel, line of, let's write best fit. Maybe it was generated by a computer. Okay, so the line of best fit is just a line that the computer generated that's trying to hit as many points as possible, right? And if it can't hit all of them, it's going to do its best job to try to keep the distance between like maybe these points above as the same distance away from the line as these points below. So it's seeking to try to draw a line through all of these points, but it can't. So because it cannot draw a perfect line, it's going to draw the best fit that it possibly can. It's going to draw the best line it possibly can to kind of separate this data into two equal halves so that each piece of data is as close to the line as possible. So the time spent in texting in hours. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as we see, the time is increasing. The time they spent exercising looks like it's decreasing. And that would make sense. The more you text, the less you're going to exercise, right? You can't kind of text and exercise at the same time. So each of these pieces of data are representing each of the 21 students. So we have some fill in the blank here. For each of these 21 students, as time is spent increasing or time spent texting increases, the time spent exercising tends to increase, decrease, or stay the same. Circle one. Okay, we know as the time is increasing, the time that these people have spent exercising is decreasing. For each of these 21 students, there is a positive, negative, or no correlation. We're going to circle one between time spent texting and time spent exercising. Well, we know this is a negative correlation. Using the line of best fit, we would predict that a student texting for 6 hours would exercise for approximately 1.8 hours, 2.6, 3.4, 4.2, or 5 hours, circle one. Okay, let's get real close here. For student texting for 6 hours, what could we predict? Let's come up here and see what the line of best fit would tell us. That they would be somewhere here. And let's come across. So somewhere between 4 and 5. So probably we would circle 4.2 hours. That we could predict that a student who spends 6 hours texting would exercise for approximately 4.2 hours. All right, our last concept is computing residuals. So we have a table and scatter plot showing time spent studying, which they're calling X, and their midterm scores, Y, for each of the 10 students, or 10 students have been selected. And it looks like they've tracking how much time they spent studying against their midterm score. Okay, so before we even look at this, let's just take a look. We see we have a positive kind of trend happening here. So as time spent studying is increasing, 2, 4, 6, 8, 10 hours, we can also see that the midterm score is also increasing. Okay, which would make sense. In in general, the more you study for a test, the better that you're going to do on the test. All of these little points are all represented by these coordinates right here. So if you spend 3.3 hours studying, we would predict that your midterm score was 23.83. So 3.3 right here, hours studying, you're coming up to right around a 23.83 midterm score. They give us an equation. The equation of this line, this is that line right here that the computer is trying to make. It's trying to hit every data point, but it can't. So it's doing its best to try to eliminate the gaps, like the spaces between like this point and the line or this point and the line. It's trying to decrease that or keep that as minimal as possible. All right, it's doing its best job to do that. By the way, those are called residuals. Right? From what the line actually predicts could happen versus what they see actually happening in the chart. So we have an equation of a line that is y equals 4.5x plus 10.54. That's this equation right here. Use this equation of the line of best fit to fill in the blanks below. Give exact answers, not rounded approximations. All right, we have a chart to fill in. So here's our chart. We've got time spent studying, 11.9 hours. What was the observed midterm score? So we're going to get this from the chart. The predicted midterm score, we're going to use our line of best fit. And the residual is going to be the difference between the observed midterm score and the predicted. That probably isn't spelled right. I'm sure no one cares. Okay, so let's take this 11.9. Let's start with that. So what the person that spent 11.9 hours, What was their midterm score on the chart? Let's go look. So this person spent 11.9 hours studying and they received a 70 on the midterm. Okay, that's going to be a 70. Now, what's the predicted midterm? Well, 11.9, it's going to be hard to see without that line of best fit. 11.9 hours is almost 12 hours, so you can kind of eyeball up here and then kind of come across here. But we really don't know what that point is. It's between 60 and 70, but we're going to use this line of best fit. So we're going to use y equals 4.5x plus 10.54, and we're going to plug in 11.9 in for x. We're going to plug in 11.9 hours, multiply it times 4.5, and add 10.54, and that's going to give us the predicted score. What that line thinks, right? This what the line thinks that the person they would predict the person to get if they spent almost 12 hours studying. All right, I got to break out my calculator for this one. Let's find it here. Okay, so 4.5 times 11.9, hit equal, and add what, 10.54? Oopsie. Well, the line of best fit would predict that that person would get a 64.09. So that's the predicted. Okay, now the residual is the difference. So what are they looking at? The difference between the 70, right, that that person did get and what they predicted them to get. There's that difference there. So all we need to do is subtract 70 minus 64.9. 64.09, excuse me. That'll give us that residual. Well, the difference between what actually happened and what was predicted to happen. 5.91 is our residual. All right, let's do this all over again. The person who spent 18.1 hours studying, what would we observe that they got on the midterm? Well, they got a 91.99. Okay. What would our line predict that a person who studied 18.1 hours would get? Well, 18.1 hours is something right here. Well, if we bring this up, see where it slams into this line and comes across, what would it predict? Somewhere between a 90 and a 100. But this line goes with this equation, so we're going to plug in 18.1 into this equation to see what the line thinks that that person should get, predicted that they should get. So we're going to do y equals 4.5 times 18.1 hours of studying to get the predicted score. We know what happened. That person got a 91.99. But what does the line think should have happened? So 4.5 times 18.1, oopsie, hit enter and add that 10.54. It would predict that they would get, oh, a 91.99. Perfect. Notice that what the person got in actuality and what was actually predicted to happen are the same. So there really is no residual between the two. So 91.99 minus 91.99 equals 0. Okay, so that line was actually perfect. The prediction was actually true. It was perfectly the same as actually what happened. All right, are we down to our last slide? We are. Okay. The last piece is identifying correlation and causation. Here's just some notes that I wanted you to have. Two quantities have a correlation if they tend to vary together. Here's an example. Suppose there are more bees in a yard when there are more flowers. Then we see that there is a correlation between the number of bees and the number of flowers. Suppose less coffee is consumed when the temperature is higher. Then we see a correlation between the amount of coffee consumed and the temperature. Causation means that a change in one quantity directly causes a change in others. So more flowers cause a change in more bees. Temperature is lower, that means coffee consumption is lower. Keep in mind, correlation does not always imply causation. That is, two quantities can vary together without one of them actually causing a change in the other. So just be careful. Correlation does not always imply or have a direct result, and that's called causation. Here's some practice problems. Let's take a look at them one at a time. A car dealership conducted a survey. It showed that younger customers tended to purchase a lower price car. What is likely true? That there is no correlation between age and purchase price? That there is a correlation between age and purchase price? There may or may not be a causation. Further studies would have to be done to determine this. And there is a correlation between age and purchase price. There is probably also causation. That is because there is a decrease in the purchase price with a decrease in age. What do you think is the best answer here? Okay, hopefully you picked the second one here. There seems to be a correlation between the people's age and the purchase price of the car, but until you run an experiment, you can't really say that there's causation. So there may or may not be causation. You would need to run a further study. You would need to actually run an experiment to really say that one causes the other. We think they're correlated, but we can't really say for sure if that one causes the other, meaning the younger the customer, they're always going to buy a lower price car. Let's try this again. A doctor's office found that a lower outside temperature did not indicate a change in the number of appointments made. What can we determine from this information? So what the doctor's office is saying that if the temperature outside was low, it didn't seem to change in the number of phone calls they were getting for appointments that needed to be made. What can we determine? That there is no correlation between outside temperature and number of appointments made, that there is a correlation between outside temperature and number of appointments made. However, there is no causation. That's because there is likely an increase in the number of appointments made with a decrease in the temperature outside, or there is a correlation between outside temperatures and number of appointments made. There may or may not be causation. Further studies would have to be done. Okay, in this case, they found that there was no change in the weather and the number of appointments that were made. So there is no correlation that we have found between outside temperature and number of appointments made. One last one. A piano instructor examined students' progress. She noticed that when students spend less time playing video games, their memorization ability does not tend to change. What can she conclude? That there is no correlation between the amount of time spent playing video games and memorization ability, that there is a correlation between the amount of time spent playing video games and memorization ability. There is probably also causation. That's because there is an increase in memorization ability with a decrease in the amount of time spent playing video games. Lastly, there is a correlation between amount of time spent playing video games and memorization ability. There may or may not be causation. Further studies would have to be done to determine this. Okay, this piano instructor looked at students' progress, and she noticed that when students spent less time playing video games, it didn't change their memorization ability. So we can conclude that there really is no correlation, we don't think, between amount of time spending video games and memorization ability. So that's good news for those of you that like to play video games. Apparently, it does not affect your memorization, at least according to this observation by this one piano teacher. All right, this concludes our videos for week 12. Good luck there in the homework. Bye.